All right, so the whole goal of what we're going to add for boosting here is we're gonna expand on this notion of hardest examples and weighted mean. But before I can do that, I'm going to have to define a couple of terms, okay? And you let me know, Michael, if these terms make sense. So here's the first one. The first one is error. So how have we been defining error so far?
Usually we take the square difference between the correct labels and the what's produced by our classifier or regression algorithm.
Ah, that's true. That is how we've been using error when we're thinking about regression error. How about a notion of accuracy, about how good we are at, say, classifying examples? So let's stick with classification for a moment.
Well, so that would be the same as squared error, except that it's not really needing the whole power of squared error. That is to say, if the outputs are zeros and ones, the squared error is essentially just whether or not there's a mismatch. So it could just be the total number of wrong answers.
Right. So what we've been doing so far is counting mismatches. I like that word, mismatches. And we might call an error rate or an error percentage as the total number of mismatches over the total number of examples. And that tells us whether we're at 85% or 92% or whatever, right? So that's what we've been doing so far. But implicit in that, Michael, is the idea that every single example is equally as important. So that's not always the case. Now, you might remember from the very first talk that we had, we talked about distributions over examples. We said that, learning only happens if your training set has the same distribution as your future testing set. And if it doesn't, then all bets are off, and it's very difficult to talk about induction or learning. That notion of distribution is implicit in everything that we've been doing so far, and we haven't really been taking it into account when we've been talking about error. So here's another definition of error, and you tell me if you think it makes sense given what we just said. So this is my definition of error. So the subscript D stands for distribution. So we don't know how new examples are being drawn, but however they're being drawn from some distribution, and I'm just going to call that distribution D. Okay?
Mm-hmm.
Right. So H is our old friend, the hypothesis. That's the specific hypothesis that our learner has output. That's what we think is the true concept. And C is whatever the true underlying concept is. So I'm going to define error as the probability, given the underlying distribution, that I will disagree with the true concept on some particular instance X. Does that make sense to you?
Yeah, but I'm not seeing why that's different from number of mismatches in the sense that if we count mismatches on a sample drawn from D, which is how we would get our testing set anyway, then I would think that would be, if it's large enough, a pretty good approximation of this value.
So here, Michael, let me give you a specific example. I'm going to draw four possible values of X. And when I say I'm going to draw four possible values of X, I mean I'm just going to put four dots on the screen. Okay? And then I'm going to tell you that this particular learner output a hypothesis, output, a potential function that ends up getting the first one and the third one right, but gets the second and the fourth one wrong. So what's the error here?
So let's just make sure that that everybody's with us. Let's do this as a quiz.
Okay, so let's ask the students what they think. So here's the question again. You've output some hypothesis over the four possible values of X, and it turns out that you get the first and the third one right, and you get the second and the fourth one wrong. If I look at it like this, what's the error rate?